Vector addition by components. Our objective here, we want to add vectors graphically or by components. All right, we're going to pull in a number of ideas from previous video lectures. Let's take a look. I'll slide down a little touch here. We know that a vector, resultant vector, is made up of an x component and a y component. Okay, an x vector and a y vector. We know that the standard position angle is found by taking the inverse tangent of the y length divided by the x length. We know that when we're given a vector r, its magnitude can be found by taking the square root of the sum of the squares of its components' magnitudes. We know that to find the magnitude of the x component, we take the magnitude of the vector times the cosine of the angle. To find the magnitude of the y component, we take the magnitude of the vector times the sine of the angle. And we know to find the reference angle, which is the positive angle between 0 and 90, we take the inverse tangent of the absolute value. And we were kind of focused on this one. Y length over x length is the absolute value of the magnitude of the y vector divided by the magnitude of the x component vector. So the magnitude of the y component vector divided by the magnitude of the x component vector. So a lot of things we're going to pull in here. Be prepared. When two or more vectors are not at right angles, they can still be added. And what we're going to do is we're going to replace those vectors with their x and y components. And then we can use their components, and we can add the x components of the vectors, and then add the y components of the vectors to find the x and y components of their resultant. So we're substituting and using that substitution to do this. This is obviously going to be a pretty big deal. And we're going to do 3 examples here so you can see it. Okay, so the procedure for doing this. Okay, well, number 1, as necessary, place all vectors in standard position. As a reminder, standard position means the tails are at the origin. Number 2, as necessary, determine the standard position angles. Okay, again, a standard position angle starts from the positive x-axis and works counterclockwise. Number 3, we're going to add the x components of the given vectors to find the x component of the resultant vector. We're going to add the y components of the given vectors to find the y component of the resultant vector. We're going to find the magnitude of the resultant vector using these x and y components that we've done before. We're going to find the reference angle of the resultant vector using the x and y components and the inverse tangent function as we've done before. And we're going to use this reference angle and the quadrant, which we've done here again, as determined by the sines of the x component of the resultant vector and the y component of the resultant vector to determine the standard position angle theta. So a lot of stuff going on here. I'm going to do 3 examples. The first one I will do with a bit more detail. So let's strap in and let's take a look. Give me a moment to get my next piece of paper. This will require some space, and I'm big on having plenty of space to write on. So here we are. Example number 1, find the resultant of 2 vectors. Okay, let me make sure I can find my page here. Here we go, I'm on the wrong page in my notes. Find the resultant of 2 vectors A and B. In other words, we're going to add them. Given that the magnitude of A is 1200, the standard position angle of A is 270 degrees, the magnitude of vector B is 1750, and the standard position angle of vector B is 115 degrees. Let's draw it. Okay, so here I come. Here's my X and Y coordinate plane. Okay, A has a standard position angle of 270. Okay, so I got to go around to 270. This is 270 degrees. Remember, from the positive x-axis counterclockwise. And it's 1,200 units long. So I will kind of go like this. And this is, the magnitude of this is 1,200. The magnitude of A is 1,200. And this is, I guess this is vector A, and its magnitude, that's probably better. This is vector A, its magnitude is 1,200. Vector B, I have to go around 115 degrees. Well, this is 90, this is 180, so 115 is approximately here. Vector B is longer, so I'll go a little bit longer for vector B. Okay, and here is vector B. Again, this is 115 degrees. This is vector B, and vector B's magnitude is 1750. So there's our picture right there. Now, out of curiosity, let's take a look at this graphically. Let's take a look at adding these two graphically. Okay, so I'm going to redraw what's going on here, but I'm going to be a little bit simpler with it. Okay, so here is A, here's vector A, and here is, hope I can get pretty close to what I have there. Here is vector B. Okay, we know graphically there are two ways to add. These are tail to tail, so we can draw a parallelogram. So there is that one, and there is that. Whoops, I'm a little off. I won't draw that's probably a little bit, maybe be a bit confusing. Let's do a head to tail instead. You can draw a parallelogram, which I think would have us do more like this. There's your parallelogram. Or we can do and put this one and put it here, so I can put vector A over here. Either way, there is the resultant vector we're talking about right there. Okay, so that's what we're looking for. Find the resultant vector if we add them up. So I add them head to tail, or I can add them up in the parallelogram method. This is the resultant vector, and we can see we have a quadrant 2 angle from our drawing. Okay, and we can see that our R, our vector R, is going to be shorter than vector B. So the magnitude of R vector will be shorter than the magnitude of the B vector because we came in, so we're a little bit shorter here with R. So no matter what, the magnitude better be less than 1750. Okay, my recommendation for doing this is to create a table. Okay, so we're going to do it as follows. I'm going to draw a long line across most of the paper. I think I'm still on the screen. I'm looking at it. Yep, so I'm going to put the vector here. I'm going to have its magnitude here. And I'm going to have its standard position angle here. And then I'm going to go like this. And then I'm going to do the X component. And then I'm going to do the Y component. Okay, let's first notice something. Let's first remember, so as we look at our steps, step 1, as necessary, place all vectors in standard position, tilde the origin. So here's step 1. We put the vectors in standard position, tails at the origin. Okay, so I got vector A, vector B, I'm going to underline here, and this is going to be the resultant vector here. Okay, so vector A has magnitude 1200, has standard position angle, it's given to us as 270 degrees. Vector B has magnitude of 1750 and standard position angle 115 degrees. SP stands for standard position. Okay, so this is step 2. Get them in standard position. Let's find the x component. Okay, well, vector A's x component we find with 1200, which is remember it's the vector times the cosine of the angle. So it's 1200 cosine 270 degrees. I've already put this into a calculator and it's 0. And that makes sense. Look, the x component of this A vector is 0. It doesn't go anyplace in the x direction. What is the x component of our B vector? Well, it's going to be the length of the vector, 1750, times the cosine of its standard position angle, 115, and this one comes out to be negative 739, and I would like a little bit more space. I'm going to do a 0.6 here. Okay, so that's a little bit nicer. There we go. I'll go to there. Okay, so we now know we can add these two up, and we have the x component, the magnitude of the x component of the resultant vector. Okay, so this is a sub x plus b sub x, magnitude of x component plus magnitude of A plus magnitude of the x component of B. And we can substitute. This is 0 plus negative 739.6. And so we now know the x component of our resultant vector is negative 739.6. If we look up here, yep, the x component of r is going to be negative. We just came back here, right there. Okay, now let's do the y component. Okay, a sub y is a sine function, so 1200 times the sine of the angle. The angle again is 270 degrees. I did the math with the calculator and you get negative 1200, and that makes sense. It's down, so it's negative 1200 in the y direction. B in the y direction is positive, so it's going to be 1750 sine of 115 degrees, and we'll come out with, again I did the math, 1,586, and we know that if I add those two up, I will get the y component of the resultant vector, negative 1200 plus, whoops, let me do my other step first. Sorry about that. I'm going to add up the y component of A plus the y component of B, negative 1200 plus 1586, and the y component of the resultant vector is going to be 386, and that we know it's positive because here's the resultant vector, it's positive. Okay, so step 3 was here, find the x components of the given vectors to obtain the x component of the resultant vector. Step 4 was here, find the y components of the given vectors to obtain the y component of the resultant vector. Step 5, let's find the magnitude. We know r sub x and r sub y, so let's find the magnitude of the resultant. Right? Let's find the magnitude of our vector r. And we're going to use the, whoops, lost a little bit there. Sorry about that. Let's try that again. Let's find the magnitude. There you go. Now you can see where I am. I sometimes lose track of myself. So r is equal to the square root, and we did this in a previous video lecture, x component squared plus y component squared So r is equal to the square root. The x component is negative 739.6 squared. The y component is 386 squared. That goes into a calculator, and out comes 834. So back up here, this vector is 834 units long. At sides is 834. Now let's find the standard position angle. Okay, so step 6. Let's find the reference angle. We're looking for the direction. Okay, so we know that theta ref is equal to the inverse tangent of the absolute value of r sub y over r sub x. So theta ref is equal to the inverse tangent. R sub y is 386. R sub x is negative 739.6. Let's pop it into a calculator. Theta ref is equal to 27.6 degrees. Okay. However, we need to recognize, let's see here. So step 7 says, use this reference angle and the quadrant as determined by where it's located. Well, r sub x is negative. R sub y is positive. Well, x is negative and y is positive in quadrant 2. So we're in quadrant 2. And again, if we go back up to our drawing, we saw here we're in quadrant 2. Okay? In quadrant 2, we take our reference angle and we subtract it. So theta is equal to 180 minus our reference angle. And our standard position angle is 152.4 degrees. Okay? So, find the resultant. That was our charge. The resultant, which is this. That's the sum of these two vectors. The resultant is the sum, in this case, of A and B. The resultant has magnitude right here, 834 units, and is directed at a standard position angle of 152.4 degrees. And there you have it. Okay, so we got pretty precise with that. Now you'll notice there's a lot here. I'm going to do 2 more examples. There's a lot here. Do recognize a couple things. It sure is nice to have a picture. And I even drew a second picture so you could kind of see the graphically, we added them up graphically to get a sense. But it sure is nice to have a picture. It sure is nice to organize your work in a table. Okay, recognizing your vectors, magnitude, and standard position angles, finding the x components and finding the y components separately to get your r sub x and your r sub y. And then as we've done in the past, we just use these to find the magnitude of the resultant and then find the direction of the resultant right there. So it's nice to have things organized. I highly recommend it. Okay, let's take a look at a second example. How about one that's got a bit more real-life application? I think I'm still fine with my position of the paper here. Example 2, a person who swims 2.5 feet per second in still water is swimming at an angle of 57 degrees north of east in a stream flowing 38 degrees south of east at 1.7 feet per second. Find the person's resultant velocity. Of course, velocity we know is a vector because it has both speed and direction. I'm going to call my person vector P, and the stream I'm going to call vector W for water. Let's make a picture. Okay, so here's my, whoops, that's a crooked line. Let's get a straight line out of that one. I generally do pretty well. Okay, this is east. This is north. Okay, the person is swimming an angle of 57 degrees north of east. Okay, here's my person. This is vector P. And this is 57 degrees north of east. There's my vector. And this person is swimming this person's speed. So the magnitude of this, P, is equal to 2.5 feet per second. Okay? Now the water says it's coming 38 degrees south of east. Okay, so I got to come down 38 degrees to the south of east, and this is my vector W. Okay, and this is the magnitude of this is 1.7. So W equals 1.7 feet per second. Okay, so there's the picture. That's what we got going on here. The resultant vector. I'm not going to draw it for the purposes of time, but if we draw the parallelogram, because they're tail to tail, or we put this vector on the end of this, it looks like we're going to be in quadrant 1 with a vector a little bit longer than P. It looks like the person's kind of getting a small push from the water. So we're going to be kind of in here is my guess. Excuse me, with a bit smaller positive angle and a little longer, a little more magnitude than the person's speed by him or herself. Okay, so let's make our table. All right, long line. Excuse my sound effects. Okay, vector, magnitude, standard position angle. Okay, we'll start here. The vector, my person is vector P, my water is vector W, and I'll draw this line, and this is my resultant vector R. My person's magnitude is 2.5 feet per second. My person's standard position angle, this is simple, it's 57 degrees. The water's magnitude, well, the water is going at 1.7 feet per second. The water's standard position angle, wait a second, standard position means I start from the x-axis and I go counterclockwise. So in this case, I got to do some math. I got to do 360 minus 38, and I come up with 322 degrees. Okay, so that's the standard position angle, 322 degrees. Okay, so I got to go around to get to here, and I get 322. 360 minus 38. Okay, now let's do our x component. Or x components, I guess I should say. P-O-N. Make sure I can spell. E-N-T-S. Okay, I know that the x component of P is equal to the magnitude times the cosine of the standard position angle. And that turns out to be 1.36 feet per second. And I know the x component of the water vector is the magnitude times the cosine of its standard position angle, 322 degrees, and that comes out to be 1.34 feet per second. And so I can find the x component of the resultant vector by adding those two. The person's x component plus the water, the stream's x component. R sub x is equal to 1.36 plus 1.34. So R sub x is equal to 2.70 feet per second. That's the magnitude of the resultant vector. We mentioned that it would probably be a little bit longer than the person's vector. If we put this vector here, it's a little bit longer, and indeed it is. It's 0.2 longer than the person's vector alone. Now let's do the y components. Okay, the y components take advantage of the sine function. So the y component of the person's vector, the magnitude, times the sine of the angle, 57 degrees, and I got 2.10 feet per second. The y component of the water's or the stream's vector is the magnitude of the stream times the sine of its standard position angle, 322 degrees, and out comes, in this case, a negative, and that makes sense. The y component is negative here, so we should get a negative 1.05 feet per second. So now we can get the y component of the resultant by adding the y components of the two, and the y component of the resultant is 2.10 plus a negative 1.05. Pull out a calculator if you need to, and the y component of the resultant is 1.05 feet per second. Okay, now we're set because we know the x and y components of the resultant. We can now find the magnitude of the resultant and the direction of the resultant, like we did earlier. Magnitude of the resultant vector. Okay, the magnitude is equal to the square root of the x components squared plus the y components squared. The magnitude in this case is the square root. The x component is 2.70. The y component is 1.05. Pull out a calculator, and I get 2.9 feet per second. Okay, and again, we looked at this and we said, well, this makes sense. If I put this up here, or I use the parallelogram method, I've got a longer resultant, and sure enough, got a longer resultant right here at 2.9. Okay, let's do the direction. Okay, we're going to find the reference angle using theta ref. Find the reference angle called theta ref, and that is the inverse tangent of the absolute value of the y component divided by the x component. So the reference angle's measurement is the inverse tangent of the absolute value of 1.05 divided by 2.7. Into a calculator that goes, and out comes 21 degrees. Okay, now what do we notice? Well, the x component of the resultant vector is positive, and the y component of the resultant vector is positive. So we're in quadrant 1. Okay, so let's see here. The x component and the y component are positive. Well, x and y are positive in quadrant 1. So we're fine. We don't need to do anything. Yep, we're in quadrant 1, so theta is the reference angle, equals 21 degrees. Okay, that's kind of nice when that happens. All right, so find the person's resultant velocity. The person's resultant velocity is 2.9 feet per second. That's the magnitude at a standard position angle of 21 degrees. We go back up to our graph. Again, you can see if we were to put this here, we kind of have a vector. This is our resultant vector right here. Well, that's going to be something like this. And you can see it's going to be a little bit longer than this one, but the degrees will be less than 57, and we have it as 21 degrees. So there's the resultant vector if we add those two together. Okay, one more example, so stay with me. This we're going to have 3 vectors in this case. And I might just cut this short and let you finish it up. Okay, because once you probably have the pattern down at this point. Okay, example 3. We got 3 vectors in this case. So we're going to find the resultant vector from adding 3 vectors together. We've got 3, t, u, and v. Notice that here's t. T is on the x-axis. Its magnitude is 422. This is u. U is in the 3rd quadrant. Its magnitude is 405. And here's v in quadrant 2. Its magnitude is 210. So we want to add all 3 of those up. Same process. I'm going to draw. Wow, that's a terrible straight line. I'm going to draw a straight line. And I'm going to do the same thing I've been doing. Vector, magnitude, standard position, angle. Okay, down to here. Now I have 3 vectors. So vector t, vector u, and vector v. Okay. And then once I add those up, I'll have vector r, the resultant vector. Magnitudes, well, the magnitude of t is 422. Magnitude of u is 405. And the magnitude of v is 210. Okay, no problem there. Standard position angle, well, t is on the x-axis. Its standard position angle is 0 degrees. U is down here, and we're told that the angle from here to here is 35. So to find the standard position angle, we're going to take 270. So from here to here is 270. And we're going to subtract 35 to go backward, and we come up with 235 degrees. So again, standard position, 90, 180, 270, subtract 35 to get there. V is in quadrant 2, and we're told that the angle from V to the x-axis, the negative x-axis, is 70 degrees. Standard position requires going from the positive x-axis counterclockwise. So here's 90, here's 180, subtract 70, you get to 110 degrees. So there you are for the standard position angles. Okay, x components. Okay, well, the x component of the v vector, again, the x components are the cosine, so the magnitude, cosine of standard position angle. In this case, we get 422. The x component of the u vector, magnitude times the cosine of the standard position angle. And this one gives us a negative 232.3 if you pull out your calculator. And the x component of the v vector is found with its magnitude, cosine of its standard position angle, and with a calculator, negative 71.8. Now I can draw this line. So, how do I get the x component of the resulting vector? I'm going to add them all up. Interest of time, add up all those, and that comes out to be 117.9. Now let's do the y components. Okay, the y component of the t vector is the magnitude times the sine of the standard position angle, which is 0 degrees. With a calculator, that's 0. the magnitude of the y component of the u vector is the magnitude times the sine of its standard position angle, 235 degrees, and that comes out to be negative 331.8 with a calculator. And the magnitude of the y component of the v vector is the magnitude times the sine of its standard position angle, 110 degrees, and that comes out to be 197.3 with the calculator. How do I find the y component of the resultant vector? Well, I'm going to add them all up. The y component of t plus the y component of u plus the y component of v, and with a calculator, that comes out to be negative 134.5 units. Okay, and so we're right back where we want to be. I'll continue this quickly. How do I find the magnitude of the resultant vector? Do the same thing I've been doing. Once I get these two numbers, I'm off and running. So the magnitude of the resultant vector, adding them all up, how long is that vector? Well, r is equal to the square root of the x component plus the y squared plus the y component squared. My r is a little sloppy sometimes. Sorry about that. That's a terrible r. Okay, and so this is the square root. 117.9 squared plus negative 134.5 squared. And calculator to the rescue. 179 is the magnitude of the resultant vector. Okay, the sum of all those vectors has a magnitude of 179. What is the direction of the resultant vector? Well, again, we're right here. This time we're going to find our reference angle. Now notice, x is positive, y is negative, so we're in quadrant 4. If I go back up to here, quadrant 4 has a positive x and a negative y right here. Okay, so we're going to make use of that knowledge. Okay, so the reference angle is the inverse tangent of the absolute value of the y component divided by the x component. So the reference angle is the inverse tangent of the absolute value of negative 134.5 divided by 117.9. Pop that into a calculator, our friend, and out comes 48.8 degrees. That's the reference angle. Okay, however, we know that our x component is positive, our y component is negative, which means we're in quadrant number 4. And we talked about that just a couple minutes ago. So our theta, we have to take 360 and subtract the reference angle to come up with the fact that our standard position angle is 311.2 degrees. Okay, just about finished. Let's write it all down. So, find the resultant. So the resultant, r, is a vector with magnitude 179 and is directed at a standard position angle of 311.2 degrees. There you have it. That was a long video lecture, a long lesson, but I wanted to get through the different examples with you. Again, note Very, very nice, important to make use of a table or a chart or however you want to call this to organize yourself, and very, very nice to have a graph that you can see to make sure that things are kind of making sense as you work with them.